loud. All right. Can you hear me in the back? Great, thank you. Let's get started. So we're still talking about transformers today. Why are we still talking about transformers? Well, it took a while to sort of build up to this point where we had to explain all the, building blocks like attention, self-attention, and then actually go over what a transformer looks like. That took 2 lectures. But we've actually done that now, so why am I still talking about these things? Well, today kind of what I want to show you is just a few examples, pretty important examples of how transformers have been used. I think that this will start to motivate why we even started talking about this in the first place. I think that transformers are really important for you to know about because they're used all over nowadays. Transformers power Google Translate. Transformers power Google Search as a whole. Transformers are behind, all of the, different GPT models that are like, spitting out all of these realistic news articles and things like this, right? So transformers are really broadly used these days across a number of, research and commercial applications too. So I think it's quite good to sort of be aware of some of these things. Now that we kind of have an understanding of, what a transformer actually looks like and all of that stuff, let's actually take a look today at what it is that they're used for, and hopefully that'll sort of bring us full circle in terms of, helping you get a better understanding of why we've been talking about it for a whole week. So this will wrap up our discussion of transformers. This will also wrap up our formal technical content in the course. So that's very exciting. We're almost there, almost done. Why, when we have a whole week left? Well, next week, the first thing that we're going to do is we're going to have 2 pretty exciting guest lecturers come in and talk about some of the applications of machine learning for things like recommender systems, as well as education applications. So I think that this is going to be really, really exciting. That's going to be Monday and Wednesday. So I would implore you to, be here, especially if you're not here live, if you're listening to the recording of this afterwards, I would implore you to be here in person and, be a great audience for these guest lecturers. The content from these lectures can be on the exam, but they're going to be relatively high-level lectures. It's not going to be like, here's, everything about what a recommender system is or how we apply things to education. It's going to be more like, well, here's an overview, but now let's talk about some really interesting cutting-edge research in these areas. So I think that that's going to be really, really fun. But you're not expected to understand all of the nitty-gritty details behind some of these things. It's just to get you a flavor of what people are thinking about sort of on the frontiers of machine learning, get you a little sense of that, and then maybe pick up some of the high-level ideas that might show up on your final. Yes? I'm sorry? There will be a lecture next Friday. I haven't fully decided exactly what it's going to be yet, but I'll be here. I know I missed a couple of Fridays, but I'm here now. And yeah, it'll be something like maybe some summary, maybe some review, maybe some perspectives, things like this. But really today is kind of like the last formal technical piece that we're going to try to sneak in. All right, so guest lectures, Monday and Wednesday. Do be here if you can. They're going to be really fun. All right, let's go back to transformers and do a little bit of a review of what we did at the end of last lecture. So we talked about transformers and the general idea behind interleaving these self-attention layers with these feed-forward layers, so on and so forth. That was all great. And then we talked a little bit about how we can sort of build 2 different styles of transformers that are sort of useful for different things. I told you they were useful for different things, but then I didn't actually tell you what they get used for. So that's what we're going to do today. But first, let's review what they actually are. So remember, we had this transformer encoder. It takes in this sequence of, x1 through xt, maybe like a sentence or something like this, and then encodes it into what we call like a representation. That's z. It's the same length. It's also a sequence, right? Z1 through zt. And what this ends up actually looking like is just these interleaved like position-wise feed-forward layers, which are just like, these like little nonlinear layers, right? Plus these self-attention layers that actually process the whole sequence into another sequence. And you just do this as many times as you like until you get to a Z1 through ZT that you feel like you're happy with, that's going to be easy for, something to, use that and then do what it needs to do. So this becomes the idea of like having representations or embeddings or features, whatever it is that you like to call them, that get used for these downstream tasks. Today, I'm actually going to tell you what some of those downstream tasks are. So that's really the exciting part. But then we also talked about transformer decoders, right? And transformer decoders, in some sense, are perhaps a little bit easier to understand because their job is, there's only one job, and it's very clear what their job is to generate, right? Their job is to try to generate, sequences, and the way that they end up doing this is one at a time, one token at a time, right? Feeding in all of what's been generated so far, y0 through yt minus 1, and then generating the next token, yt. And then what this actually ends up looking like is you feed in the sequence so far, y0 through yt minus 1. You pass that through, basically something that looks very, very similar. And then you actually get all of the predicted next tokens like y1 through yt, right? But you sort of ignore everything except this last thing that you generated, yt. You put that back into the input, and then you run this all over again, get yt plus 1, so on and so forth. And this might end up looking something like, some sentence or some paragraph that you're trying to generate. Turns out doing this is pretty darn good at generating things that look pretty realistic. So that's kind of cool. We had this note from last time, right, about how we need to mask self-attention in decoders. We went through that a little bit quickly, so I wanted to bring it up again and just make sure that everyone's sort of on the same page about what it is that we're actually talking about here. The important bit, I was thinking this over, the important bit is that what's happening at training time with these transformer decoders is we're passing in entire sequences. Like these are just like ground truth sequences of like, sentences that you collected off the internet or something like this, right? These entire sequences are being passed into the decoder all at once, and then the decoder is basically trying to do like next token prediction. You can think of it sort of like next word prediction, right? So it looks something like this, right? Notice that I've replaced this little t with like capital T, because that's like the whole sequence, right? Minus like the last token. So that's what gets passed in to the decoder at training time, and then what it's asked to do is predict the next token after following all these things. Like what's the predicted y1 from y0? And what's the predicted y2 from like y0, y1? And so on and so forth, right? What's the predicted y capital T from the whole sequence? This is how it gets trained, right? So it's trained on capital T number of next token predictions all at once, but if we didn't have masking in this whole thing like we described last time, then what would it learn? It would just learn to predict y1 by looking at y1, right? It would learn to predict y2 by looking at y2, so on and so forth. We can't let it do that because that's nonsensical, right? Not only is the decoder not going to learn anything useful, it's going to learn something that's not even applicable at test time because it's generating its own input, so we can't feed in something that it hasn't generated yet, right? So this is why the self-attention in the decoder must be masked, which means that it has to be prevented from looking at the present and the future. We can only look at the past when actually doing this generation. And we do that masking, remember, in that self-attention mechanism by setting all of the scores corresponding to the present and future time steps to negative infinity, such that when we pass that through the softmax, we get 0 weight for all of those things, which means that the only values that we can consider are the values that correspond to previous time steps, right? So y1 is in that way only allowed to look at y0, and any yt is only allowed to look at 0 to t minus 1. That's the high-level idea. Right, so in this way, the decoder is simultaneously trained on capital T next token predictions, right? Imagine how slow it would be if instead of doing this, instead of that, during training, I passed in like a subsequence and asked it to predict the next token. And then I did that for every length subsequence, right? I've just made it capital T times less efficient to train my decoder compared to this setup where I can train on an entire sequence and then just do the masking to make sure that it's doing the right thing. That's kind of the big idea. Yes? So essentially, we're parallelizing it in this way. Exactly. That I think is like kind of the right way to think about it, right? So instead of doing all, if I didn't have masking, I would have to train on all of these different, subsequences in my big sequence, one at a time, which is just totally not worth it. Yes. Yeah, it's an interesting question. So, like, does this bring sort of like some kind of disadvantage to things like, trying to predict y1 because we have very little information to try and predict y1. We only have y0, right? But if you think about it, when you're doing generation at test time, it's the same way, right? Like when I'm generating y1, when the model is generating y1, it only has y0. It doesn't have anything else, right? So this is just sort of mimicking the, the kind of way that the model is actually going to get used. I started telling you last time about what this original transformer actually looked like. Okay, now we're past the review. Now we're getting into all of the models, all of the transformers that people have actually built for doing different things, right? And I started telling you last time about this original transformer paper, which is this 2017 paper that's cited very small in the bottom left, but you can go look at these slides later if you want to go read that. It's actually a great paper, so I would encourage you to read it, because I think that it's written pretty clearly. And I told you how this transformer follows this sort of encoder-decoder architecture, which basically means that it's both an encoder and a decoder. So it's got a piece that's a transformer encoder. It's got another piece that's a transformer decoder. And its purpose, right, this transformer was originally designed to do machine translation, right? So like translate one language to another language. And so the first piece that we had in this transformer was take in a sentence, right, in some source language, like maybe like English, right? So that's what the X1 through XT are. It's like tokens that represent a sentence in that source language. And the encoder is actually going to turn that into some representations, Z1 through ZT. This is not the translation itself. This is sort of just some representation that we've built of the source language, of the source sentence. The thing I haven't really told you yet exactly how it works is that the decoder, when it's trying to predict or trying to generate the target sentence that corresponds to the translated version of the source sentence, it's going to be doing that generation that we've already talked about, right, this autoregressive generation, but it's somehow also conditioned on these representations Z1 through ZT in order to know what it's even trying to generate, right? If there was no arrow from Z to the decoder, then the decoder would just be doing unconditioned generation. It'd be trying to generate whatever it wants, right? When we condition it on Z1 through ZT, now its goal is to look at those representations, which give it information about the source sentence, and actually do the translation from the source sentence to the target sentence. That becomes its goal, right? So this is kind of the high-level idea. This is a sequence-to-sequence model that follows this encoder-decoder architecture. The encoder sort of processes the source sentence, and the decoder, conditioned on those processed representations, then generates the target sentence. Yes? Great question, great question. So when I say conditioned on, do I mean somehow that like Z1 through Z capital T is becoming like the Y0 that gets passed into to the decoder? So in this model, that's actually not how it's done. And I'll show you on the next slide exactly how it's done. However, what is interesting is that we can imagine that maybe if we didn't have the encoder at all, maybe we could get just a decoder to also do translation by basically passing in information about what we wanted to translate into Y0. So we're basically prompting it in this way. People have explored this for certain models, like GPT is kind of able to do a little bit of translation, even though it wasn't even trained to do that. So that is kind of interesting. But this type of model turns out to be much more effective for translation in particular. And this is the kind of model, like a very, very large version of this model is actually what powers most of Google Translate. Yes? Good question. I don't remember why this line is red. I think it's red because I was just trying to say that like the transformer decoder's own output is being fed back in as its input, right? So after it generates some YT, that YT gets appended to the input, and then it's run again to get YT plus 1, which is appended, and then so on and so forth. Oh yeah, so right, so maybe this diagram is not super clear. It's totally not clear, but so Y0 is usually like some special token like start, right? So this is the Y0 is not something that the decoder actually generates. So the decoder, the first time step is going to get Y0. It's just going to generate Y1. Okay, this Y1 then becomes the thing that gets appended to the decoder's input to get Y0 and Y1. That becomes its input, it gets passed through again, and it generates Y2. It actually also generates another Y1, right, because it's doing both of those things, right? Like, but we ignore that Y1 that it generates because we already got that part, and then we just take the Y2 that it generated and then stick it back onto the input. And now we have Y0, Y1, Y2 that we're passing through in order to get the decoder to generate Y3, and then so on and so forth. You know, capital T number of times, or until we're satisfied with like this sentence that the transformer is generating. Is the input of the decoder the same size each time? Technically, yes, it is. What we do is we just like pad whatever we don't have. So like we're always passing in a sequence of length capital T, but if we only have like one token so far, all of the other ones are this like special pad token that means like there's nothing here yet. And then that pad token also tells us which parts of the output to ignore, because accordingly, all of those pad tokens are going to generate like tokens that we don't care about. So what are the pads specifically? The pads are like, so I didn't talk about this in detail, so it's okay if this part doesn't make sense, but basically all of the things that you're passing into like a transformer, if it's dealing with language, is a one-hot vector. And the size of that vector is the size of your vocabulary. So you can almost think about it like the number of words that you have in English. It's not exactly that, but you can sort of think of it that way. You can just make that vector one longer if you also want to include like a pad token, and then that becomes like a 1 down there, and then zeros everywhere else becomes like the special pad that you pass in to denote that you don't have any input there yet. Yes. Right, right. So we had this question already about, is Y0 the thing that's containing all the information about the source sentence, like Z1 through Z capital T? Here it's actually not that. And Y0 is actually literally just like a start token. I'm going to tell you on the next slide how we actually incorporate information from Z1 through Z capital T into the decoder such that it actually knows what sentence it's trying to translate. Yes. Things like grammar and syntax, are these all worked out by the decoder? Pretty much, yeah. The encoder's only job is really to just sort of like summarize what was in the source sentence. It's the decoder's job to understand how to generate valid sentences in the target language. And that it does so using its own knowledge that it built up from the training data, right? And then the encoder is really just telling it, the only thing that the encoder is doing is telling it what the source sentence was about. Okay, these are great questions. Let me tell you a little bit about how we actually connect this encoder and decoder, okay? So this encoder has given us some representation of the source sentence, right, in the Z1 through Z capital T that it output, and this decoder is going to use that. How does it use that? Well, let's say that well, I guess this is Y0 through YT minus 1. Yeah, sure. So let's say that we're, generating the very last token at this point. I think it doesn't really matter what it is that you specify. And then we have something that looks like, this feed-forward layer plus this self-attention layer. We already knew those pieces, right? The decoder If it's conditioned on an encoder, has another layer that we also stick in called a cross-attention layer, which is actually what's going to bring in that information about Z1 through Z capital T. So this cross-attention layer is where Z1 through Z capital T comes in. It's called cross-attention because it's also attention, right? So it uses like a very similar like key query value system, query key value system, right? It just, all that differs is like where you get the inputs from, right? So the query is going to come from, you know, the own sequence that the decoder is processing, right? But the keys and values are going to come from this representation that we're getting from the encoder, right? So in that way, this cross-attention layer is taking in information that was, you know, the result of the encoder processing the source sequence, right? And it's going to turn those into keys and values that the decoder can then query and ask for in order to figure out, hey, what should I even be saying? You know, what is the content of the source sentence? Now let me actually, you know, figure out what that is in order to know what I'm supposed to generate as my target sentence. That's the basic idea. So basically, when we have transformer decoders conditioned on transformer encoders, we bring in this cross-attention layer that actually connects the two pieces. When we have just transformer decoders without an encoder, there is no cross-attention layer, right? Because there's nothing to condition on. But when we have these two together, there's this additional layer that we have. We can do this as many times as we want, so the cross-attention can come in multiple times. And then we just basically have now, instead of a block of 2 layers, feed forward and self-attention, we now have a block of 3 layers, feed forward, self-attention, and cross-attention, that we then just replicate as many times as we like 6 times, 12 times, whatever, in order to get, you know, this sentence that I'm trying to output at the end of my decoder. Right, so that's how we actually connect the encoder and the decoder. Y0 in this case is still just as simple as like some start token or something like that. It's these cross-attention layers that are bringing in the information from the source sentence via the representation that the encoder generated. Yes? Yeah, good question. Right. What's the use of having multiple cross-attention layers? I think theoretically, maybe nothing. Like you're right, like as soon as you bring it in once, you have that information. But maybe like as you go through more and more layers of processing, it's possible to like lose that information via the processing that you do. So maybe sort of like refreshing that information every block is still useful in that way. Now you pretty much know how Google Translate works. This is pretty much, you know, the core, the heart of the technology, at least, you know, since like 2018 or so. Generates pretty good translations. It's basically just a very large transformer. I believe it's still, in 2022, it's still a transformer encoder plus decoder. Just a very large one. Doing pretty well. Yes. Before 2018, for a while, it was you know, this particular type of LSTM, so like a recurrent neural network, basically. It was some fancy bidirectional sequence-to-sequence LSTM kind of model. It was also like probably an encoder-decoder kind of thing. So like the difference is like, you know, the architectural change from RNNs to transformers. If we want to talk about like statistical machine translation, like, you know, word matching and bigrams and all this other kind of stuff, that's like a while ago. Like it hasn't been like that probably since, you know, at least 2014, if not earlier. Cool. So that's the original transformer. It's an encoder and a decoder. This is sort of what the original paper suggested, and they showed that this type of structure was really, really good at doing machine translation in particular. But I think that one of the really interesting things is people read that paper and they went, wait, transformers, this architecture is really interesting. Like this idea of having self-attention layers instead of like any kind of recurrence, this is really, really cool. maybe we can do a lot more with this idea beyond just machine translation. Okay, so this is basically what ended up powering a huge amount of natural language processing research over the last few years, as well as, applications of this to, sort of commercial applications and things like that. So one of the things that people sort of figured out maybe like a year or two after the original transformer was proposed was that having just an encoder turns out can be really, really quite useful too. And so one of the papers that showed this was a paper that proposed this particular model called BERT. It stands for bidirectional encoder representations from transformers. You don't need to know that. You also don't need to know why they, specified bidirectional. That's sort of a historical artifact. But BERT is this really interesting model that basically is processing language into representations, and it's just a transformer encoder. This is basically all it is. It's a pretty large one, but at the heart of it, it's just what we've learned already. So the way that they drew BERT, this blue box, it corresponds to this green box that I've drawn for you previously. It's just transposed. So it's like going like down to up instead of like left to right, okay? But at the heart of it, really all that's going on here is taking in some source sequence, or taking in some sequence like x1 through x capital T, and then processing that through a very large transformer into some representation z1 through z capital T. This is basically what BERT is doing, okay? So BERT, this is all it's trying to do. It's just an encoder, so then one might ask, well, if it's just an encoder, then how do I even know what to train this with? Like, what is the objective? If it's outputting z1 through z capital T, how do I define whether or not those representations are good or bad? Well, this is a big area of unsupervised learning, right? We've learned a little bit about unsupervised learning in terms of like, when we don't have labels, what should the objective be? Well, the objective that people defined for BERT was pretty heavily, it was inspired by sort of like what people know about the structure of language. Okay, so if I put in a whole sequence into BERT, well, if that sequence is some kind of sentence, right? Well, sentences have sort of like this temporal coherence, right? Of like, if I'm missing a word, I should be able to figure out what that word was just by looking at the words around it, right? That's a form of language understanding, right? And also this other thing about, well, if I pass in two sentences and they're like, pairs in the sense of like one came after the other, I should also understand that there's some sort of entailment or some sort of relationship between these sentences. Compared to if I just took two random sentences and then tried to put them together, there's not that kind of relationship, right? So people understand these things about language, and then they figured out, well, maybe I can train a model like a transformer encoder to basically do that same thing. So during training, which is basically unsupervised, there are no labels going on here, right? What we're going to do for BERT is we're going to have it predict some words. So some of these input tokens, right? Tokens are not exactly words, but close enough. Some of them are randomly masked, okay? So we pick basically 15% of the tokens in the source sentence to mask, and then what we want to do is we want to be able to predict those tokens that got masked using the representations that BERT generates, okay? So going from x1 to x capital T, right? Well, what's the first thing? Well, some of those x's are going to get masked, right? Which means that we replace them with this special token called mask, right? Which basically has no information about what that token originally was, okay? So we're getting about 15% of those x's just gone, okay? They're replaced with mask. We pass that through our encoder, our BERT, and then z1 through z capital T are the representations that we're getting out. Basically, what we want to be able to do is from those z1 through z capital T, recover what the masks originally were. And the way that we do this in particular during training is we slap on like an additional, like very small, like, nonlinear layer to each one of these z's. And then we try to get this layer to then predict what was the original token given this z that I have. So basically what's going on here is this representation is now capturing some notion of, these tokens, right? It's understanding what the different tokens are, and it's also starting to understand what are the different relationships between the different tokens that I have in my language, right? Because I have a mask. The only way I can figure out what that mask originally was by looking at the words, the tokens around it, right? In order to figure out, well, what word might I be missing here? So then by being able to do this, this model is then in this completely unsupervised way learning something about the structure of the language and also something about the semantics of what different tokens are going to follow each other. That point is important. So see some confused looks. If there are any questions, now would be a great time for them. Okay, so you're missing about 15% of those X's. The transformer processes that entire sequence, right, along masks and everything. That transformer processes that entire sequence into Z1 through Z capital T. And it needs to do so in such a way that from each one of those masked positions, we can use that Z to recover what the original token was. And it can only do this by synthesizing information across the entire sequence in order to sort of fill in those blanks, right, in such a way that we're going to be able to sort of, recover those original tokens. Okay, but that, oh yes. Why is it specifically 15%? Good question, I don't know. 15% seems to be a pretty good number for language in particular. You are missing a substantial amount of, the words in your sentence, but not so much that there's a lot of ambiguity behind what the original sentence should have been. So you're kind of missing words here and there, tokens here and there, right? But you can adequately fill those in with the tokens that are still preserved around it. Yes? Yeah, so this is a great question. So the loss, or at least this part of the loss, as defined for BERT, is we're only trying to predict the tokens that got masked, right? So for every single position that was masked, look at that corresponding Z, process that using some very small network, basically another feed-forward layer or something like this, right? And then have it predict what the original token was. That's just a softmax classification at the end, right? Of size, vocabulary size. Have it try to predict what the token was, and then that's the loss is averaged across all of those masked positions. So we're not trying to predict tokens for things that weren't masked, right? That's very easy, right? You just look at what the original input was. So we only calculate loss for the positions that were masked. So we only pass in the masked positions in the final layer. Yeah, basically that is correct. Yeah. So we basically only take those tokens, those Z's corresponding to masked positions, and then pass those through this final layer after the Z's, right, in order to get our predictions, which we then average together to get our loss. Yes. Should the final Z's look like what you would get if you didn't mask anything? That's an interesting question. I'm not sure I can answer that totally confidently, but it seems that way, right? In the sense that the Z should be sort of synthesizing information across the whole sequence in order to, not just say hey, I don't know what this is because it was masked. Say oh, I can look at the context to try and infer what this missing token was, right? So in that sense, it does seem intuitively like it would be generating a representation that's pretty similar to what would have happened if it wasn't masked. Yeah. If you feed in the same input tokens but mask a different 15%, yeah, good question. So it is indeed the case that sort of like every time we feed in an input sequence, that we're randomly masking out a different 15% of it, right? Is it possible that because we've seen this sequence before and saw those tokens unmasked at one time, that it could just like learn how to like memorize these things? Potentially, but you know, these things are trained on such large data sets with like proper regularization and things like this that kind of thing doesn't really seem to happen, at least not as far as I know. I forgot to say this. This gets you what we can consider to be basically like word level representations, right? So each one of these Z's, it's actually like a token level representation, but this, you know, this distinction is a little bit pedantic, right? So basically, each one of these Z's, Z1, Z2, Z3, so on and so forth, gets you a representation of, you know, that particular token at that particular time step, right? Or at least we approximately think that this should be the case. So then that's why, you know, each one of those Z's, when we pass it through some other very small, like feed-forward layer or something like this, should be able to recover what that original token was if BERT is doing its job properly. So that's quite cool. It's great to be able to get word level representations, but sometimes that's not all we want, right? Sometimes we want a representation that's like an aggregate representation of the entire sequence, right? Maybe we want to take that sequence and do something like sentiment classification or things like this that only requires a single representation that I can use for the entire sequence. So one thing that, you know, the original BERT also does is pass in pairs of sentences. Okay, so these pairs of sentences are either coming right next to each other in the training data set. Okay, so they actually are pairs of sentences, or it's like a random pair of sentences that comes from like random different places in your training data set, so they don't have any relationship, right? And then what the model needs to do from this information or from this you know, pair of sentences is try to predict, do these sentences actually come together in my training data set or do they not? Okay, so this is in some sense trying to learn some amount of you know, sentence level reasoning and you know, higher level reasoning than just doing reasoning across different words. One thing that I will mention here is that sometimes when people train these BERT models, they don't do this anymore. They kind of found that like word level representations are like the really important part. But nevertheless, at least the original BERT did do this. And then that basically goes along a very special token that's at the very beginning of this model. So you append an additional token to the beginning of your sequence. It's that orange one over there, or the thing that I outlined in the orange box, which is basically like this classifier token, right, that you're passing in, and then that first representation that you're getting out, like we can call it like Z0 for it to be special, right? This Z0 is what we're trying to use in order to predict this, this pair of sentences task that we have here. Why Z0? It doesn't actually matter which one, right? Because all of the Z's can look at all of the different X's in order to produce representations. There's no masking going on here or anything like that, right? Every single Z has access to the entire input sequence, so we just picked Z0 to be special, but it doesn't really matter. You could probably use any other Z, and as long as you train it in that way, you're going to be fine. And this is kind of what we think gets us these sentence level representations that can sort of summarize across the entire input sequence in order to get, you know, one representation that we can use for these type of aggregate tasks. But as I've said before, people have found that this is not super important, at least not all the time. Sometimes you can just use one of these other Z's and then try to do the same thing, like use that as your single representation. That seems to work okay, at least a lot of the times. All right, so why am I telling you about BERT in particular? BERT's found a lot of uses. I think a version of BERT actually powers a non-trivial amount of the Google search process in terms of taking in that query that you input and then actually processing it into something that's going to be a little bit easier to sort of synthesize and then gather results for. So transformers are really all over the place, and some of these, you know, special transformers have really found their way into a lot of different applications. Why? Well, it's because BERT turns out to be really good at solving a lot of different types of natural language tasks. And to tell you a little bit more about that, first I have to tell you about what those tasks are. So one set of tasks that people have come up with for sort of like measuring and evaluating performance on natural language is called GLUE, Generalized Language Understanding Evaluation. There are new versions of GLUE and also other types of benchmarks like super glue and all these other types of things. But GLUE is sort of a standard one, and it's good to know a little bit about. So in natural language understanding, we can pose lots of different types of natural language tasks that we might want to solve. This is a sort of a partial list of what it is that we might be interested in doing, right? So for example, this first one, it's called the corpus of linguistic acceptability. It's basically a binary classification task that's given a sentence, is the sentence acceptable, which I think is basically roughly a fancy way of saying, is it grammatical, okay? So for example, we can have examples like, books were sent to each other by the students, that's not acceptable. She voted for herself, that is. I saw that gas can explode, also acceptable. So these types of sentences, and then trying to figure out, are those sentences, roughly speaking, grammatical? There's some other types of tasks, like for example, something called natural language inference, NLI, where you get two sentences, okay, a premise and a hypothesis, and then you have to figure out, does the premise entail the hypothesis, or does it contradict, or is it neutral? So I can't perfectly say either entailment or contradiction. So we can have things like, for example, yes, now you know if everybody in August, when everyone's on vacation or something, we can dress a little bit more casual. And then that's the premise, and the hypothesis says August is a blackout month for vacations in the company. That's a contradiction because the premise already said everybody in August is on vacation, right? So it can't be a blackout month, right? Or something like, at the other end of Pennsylvania Ave, people began to line up for a White House tour. And then the hypothesis is people formed a line at the end of Pennsylvania Avenue. That's entailment because the premise already told you that the hypothesis is true, right? So basically this becomes a three-way classification task of, does the premise entail the hypothesis, or does it contradict, or we can't determine one of those, we can't determine either of those with perfect confidence. So it's all of these different types of natural language tasks that people have collected into these different benchmarks that are trying to measure these models that work on language, how well do they understand language, right? In all of these different ways, grammaticality, semantic entailment, all of these other types of things, right? So this is kind of like a big area in terms of how we actually measure performance of these language models. And BERT's like really good at all of these different tasks. Okay, that was kind of the big finding from this like 2019 paper that proposed BERT, was that BERT essentially can be used to solve any one of these tasks with remarkable accuracy as long as you do a little bit of fine-tuning on that task after this step that I've told you about. What does that mean? Basically what it means is first we're going to pre-train BERT in the way that we just talked about. We're going to mask out some tokens and ask it to predict them, and then we're also going to try to predict whether sentences follow each other, all of that type of stuff, right? After we do, and maybe I should say, this pre-training step, we can be using like billions of sentences, right? We could be using this massive data set that we collect off of the internet. We don't need labels, right? All we need are the raw sentences, and then the unsupervised objective builds itself by masking out different tokens and things like this. So that means that we can be using whatever data, whatever sentences we collect off of the internet, well, maybe not anything, but a lot of that, right? And then that allows us to have a really scalable way of training models on really, really large data sets. As long as we don't need labels, that's fairly easy. The expensive part then becomes the fine-tuning, where basically, after I have this pre-trained BERT model, I'm going to fine-tune it. I'm going to specialize it to every single one of these tasks that I have, like acceptability or natural language inference or all these different types of things, by basically training it on that little training data set that I have for each one of these tasks. Okay, I'm going to train it using the standard things that we talked about already, like backpropagation, gradient descent, all this type of stuff. I'm going to train it a little bit in order to try to make it good for that particular task. I'm going to do this separately for every single task that I have. This is the pre-training fine-tuning paradigm. Okay, pre-train on a very large unlabeled data set, okay, and then fine-tune it with a whole lot less data, right? It might only be like hundreds or thousands of examples for each one of these tasks, I know maybe that doesn't sound small to you. It's really tiny when it comes to these things like transformers. A lot less data, but that data is specific to the task that you're trying to solve. Okay, so this pre-training fine-tuning turns out to be really effective, and BERT's really good at it. In particular, BERT, as it's designed architecturally, makes it possible to solve lots of different types of tasks. So for example, if what we need to do is take in a single sentence, like corpus of linguistic acceptability, it's taking in a single sentence and deciding is it acceptable or not, right? We're going to take in a single sentence, and then we're going to output a single class label. Okay, and that class label is going to be that first Z0 thing that we talked about that then gets used on top of a classifier in order to figure out, is the sentence a 1 or a 0? Is it acceptable or not acceptable? But that's just the top right here, right? There are a lot of different types of things that we could also imagine doing. Like, for example, natural language inference involves taking in two sentences. Taking in two sentences and then making a single classification, right? How do we do that? Well, we also have a natural way of feeding in two sentences to BERT. That's how it was trained, right? And so this becomes like the top left, where we feed in both a premise and a hypothesis, and then we use that same first classification token to then make our decision about that, right? So this architectural design behind BERT also makes it possible to use across all these different tasks that have different inputs and outputs, different interfaces. BERT is sort of more general and can handle all of these different types of interfaces. And it can even do other things like, for example, part of speech tagging, like this entire sentence, this is a noun, this is a verb, this is an adjective, so on and so forth. It can do that because it's generating word level representations for every single word, every single token that you passed in, right? So it can do all of these different things because it's a very general model that just takes in a sequence, outputs a sequence, and then we're assigning meaning to those sequences afterwards based on the task that we're trying to solve. So this pre-training fine-tuning with the BERT model turns out to be really, really, really good at solving a lot of these different natural language tasks, and that's what really motivates people to study models like this. They turn out to be very general models that can solve a wide variety of things. As long as you do a little bit of fine-tuning, then these models are really, really effective at not just one thing, but really a lot of things across the board. That's kind of the power of it. Feeling like I'm doing a lot of rambling today, and we're almost out of time, but I just want to tell you about one more thing, because it's going to be, I think it's going to be on your homework. And that's this idea of vision transformers, okay? So people design transformers for language in particular and sequential data, basically. But then they realized, well, actually, this model is so good, I don't even have to use it on just sequences. I can take non-sequential data, pretend it's sequential, and then throw it into a transformer, and that's going to work really well too. So people did this for vision in particular. They did it for images using this model called a vision transformer, or a VIT. Basically, the idea is that this is just a transformer encoder. It's taking some sequence, x1 through xt, and then outputting z1 through zt. Okay, the same thing that we had before. But what's going on is that the input is actually an image. So how do we turn an image into a sequence? Basically, this image gets split into patches. So if I have that image over there in the bottom left, maybe I split it up into 9 different patches as like a 3x3 grid of my image. And then I just, turn that into my quote-unquote sequence, right? So it's going to be like a sequence of length 9 in this example. Usually it's a lot larger than that. And then we project down all of those different patches using some linear projection. Sometimes it's a convolution projection, things like this. And then these are combined with positional encodings like we talked about before, and then fed into the transformer encoder. And then a neural network, here it's called an MLP for multi-layer perceptron. I don't know if we ever learned that term, it's not important. But this neural network on the very first special position is then used to learn how to classify the image, okay? So this is basically the same transformer that we had before, but somebody decided, hey, this thing's so good, let's try it on images too. And as it turns out, doing it in this way, like patching your image, and then pretending that it's a sequence and passing it through your transformer, can also work really, really well. Okay, so I think, let me just show you a summary slide, and then we'll wrap it up. And if you have questions after, definitely feel free to come up. Transformers are this latest and greatest model for sequential data. And the fundamental building block, as we saw on Monday, is this self-attention module, which basically allows us to process this whole sequence all at once and capture all these different dependencies, summarize information across time steps, which turns out to be really, really powerful. And compared with previous sequence models, which we didn't talk all that much about, turns out that we can capture all these long-range dependencies much better using this type of approach. And even data that is not obviously sequential, like images, turns out we can benefit from the idea of transformers as well, just by pretending that the image is a sequence, passing that through the transformer like we would any other sequence, and then reaping the rewards, because this architecture is just so darn good that we get a lot of benefits in a lot of different places. So I think that one thing that this lets us think about is what else might be out there in terms of, maybe other architectures that are even better that we just haven't discovered yet. So I think that this is kind of the big question, one of the big questions that's going on in deep learning. And if you're interested, that would be one of the things